Hello there. In this video, we're going to take another look at Ciw, the Python package for especially queuing network discrete event simulation. So in this example, we're going to look at a type of routing behavior called join shortest queue. But before we get to that behavior, let's look at kind of the default behavior and point out a problem that the join shortest queue type of routing behavior solves. So here we're defining a network model where we have arrival distributions at the first of three nodes and no arrivals at the other nodes. And then we have service distributions that have these different rates of completion. The arrival distribution node has the service distribution with a much higher rate of 25, and then unequal but not quite as different completion rates at nodes 2 and 3. So for the routing behavior in this default or starting example for comparison, we're going to have that if a customer is leaving the first node, there's a 50-50 chance of them going to either of the two other nodes. And then once you're leaving one of the other nodes, you only leave the entire network. You don't go back anywhere. Okay, and we're going to ignore these comments, which really implement the new behavior, and we'll just uncomment that later. And then we'll have the number of servers at each of these nodes is just one for mostly the mathematical simplicity of understanding what's going on, one server per service. So we're going to set up a simulation here. We are going to set a seed for just being able to, so you can reproduce the same results if you wish. And we define a simulation object, mostly for some plotting stuff. I still don't think we've talked about trackers explicitly in this YouTube tutorial series, but we'll get there. Of state trackers, of basically recording information about the state of the system as it goes along. And we'll run the simulation for 80 units of time. We'll collect some timestamps, not timestamps as in ordinary calendar, but maybe I should just say the times in which the states transition in some way. And the number of individuals at the two respective downstream nodes from the arrival node. Okay, and then we'll just plot these series. So let's take a look. Let's just copy that pane, and we will run our join shortest queue, which right now does not do join shortest queue. This is just the regular queuing behavior that you get. And let's run that. So I have not thrown any axes on this plot, but it's not very complicated. So on the horizontal axis is just time as time goes on, and the vertical axis is the number of customers at that node. So you can see that node 2, which has a higher rate, that's the orange one just for reference, is actually lower in the population size, and that's because it has a higher rate than node 1. Node 1 being the blue series, that the population is larger because they're both receiving the same demand, but one has a higher rate. So you can see there's these kind of times where maybe the second node, or sorry, the first node kind of falls behind a bit and it catches up and then it falls behind again, where the higher rate of 8 here is a little bit more stable. You also get these little bumps, but you know, that's pretty normal. But the point is, of which you can see with your eyeballs, is that maybe extra demand is going off to node 1, and that node 2 probably has the capacity to take up some of that slack because it completes units of work faster. So maybe it should receive more of the flow. That's what the join shortest queue will help us do, is that at each of the two nodes, we've got those waiting areas that we're calling queues, and that customers from node 1, the one that we're basically using to provide arrivals, can change how it sends the demand to the other two nodes. So let's get rid of that routing behavior, and we'll instead specify, uncomment this one, of a network routing description that has these different node by node routers, where we have this join shortest queue. Initialize the routing object, and it basically takes a list of these destinations, as it calls it, which are really just the node numbers, so 2 and 3. So it sends it to 2 and 3, but it will do so according to which of those target nodes has the shorter queue. And of course, like the previous example, that when a customer is finished service at nodes 2 or 3, they just leave the system entirely. Everything else is the same. So let's make sure we have saved, and let's open up another terminal session here, and let's just quickly run this new joined shortest queue behavior. Now you can see that these two are very much more closely correlated in the completion. Maybe I'll even blow it up. All the other axes are the same. And you can see that they both end up having fairly correlated ebbs and flows that have to do with the random fluctuations in demand upstream in node 1, the arrival node. And so this is somewhat more balanced in the sense that whenever node 1, which doesn't have a fundamentally different rate, we didn't change any of the rates, when node 2 is taking on a longer waiting list, demand starts getting routed from the arrival node. Well, it's a little confusing the way I've said all this, but I get my indices mixed up is what I'm doing. So this is just nodes 2 and 3, just to be clear for what's being plotted, and that the rate is still lower at node 2 than it is to node 3. But in this join shortest queue, whenever we start to get an accumulation of more demand at node 2, that gets sent over to node 3. Now, it will have a bit of ebb and flow back and forth, but by and large, it's trying to balance the demand in terms of shortest queue. This is not the same as load balancing, by the way, in queue. We will get to that in the next video. But hopefully, this gives you a sense of what you can do with queue to do join shortest queue as a way of allocating the demand into downstream nodes from a given place that they're arriving in a network. All right, with that, I will catch you in the next video. Good luck with your discrete event simulations. Bye.